Welcome to my presentation. My name is Marian Turowski and I'm with the Institute of Automation and Applied Informatics at the Karlsruhe Institute of Technology. I would like to share with you our work on enhancing anomaly detection methods for energy time series using latent space data representations. In the energy system of the future, there will be an increasing share of renewable energy sources, and along with this change in energy supply, there is ongoing the implementation of the so-called smart grid. One key element of the smart grid are smart meters that record energy time series at various places of the smart grid. These energy time series that are recorded can, however, contain anomalies. Anomalies are patterns that deviate from a well-defined notion of normal behavior, and they can influence smart grid applications such as forecasting or scheduling, because these applications depend on the input and depend on the fact that the input data accurately reflects the typical behavior. So anomalies may limit their performance, and as a result, detecting anomalies is an important recent issue in energy systems. Typically, anomaly detection methods are directly applied to the input data, shown here, or alternatively to the input data is scaled first before applying the anomaly detection method. However, recently there have been promising performance of machine learning methods. There has been a promising performance of machine learning methods when they are directly applied to the latent space representation of data. For example, in forecasting, in offline reinforcement learning, or in path planning. The latent space is an abstract multidimensional space containing a meaningful representation of features that is often not directly interpretable. So we used this insight to propose a new approach that makes use of the latent space representation. Our idea is to convert the input time series containing anomalies into the latent space and use the resulting latent space representation as input for the anomaly detection method, so that method can detect the anomalies in the latent space representation of the input data. So let's have a closer look at how we obtain such a latent space representation. What we do here is that we want to find the mapping between the original realization space X and the latent space Z. So we want to find a function that maps X to Z, and to ensure that this mapping represents a known and tractable latent space distribution. In the latent space, it should be realized with either a variational autoencoder or an invertible neural network. Since we want to consider typical features of energy time series that are daily, weekly, and yearly patterns, we consider conditional versions of these neural network architectures. Let's have a look what implications do this have. So what we actually need is a trained generative method to transform the input time series into the latent space and to obtain the desired latent space representation. So how do we do the training? A few words on this. So as an input, as I said, we use conditional information, in this case calendar and statistical information, together with the input time series for training, which is used after sampling it. And using these inputs, we use a loss function, of course. The neural networks require a loss function to learn the mapping, and we have to distinguish here the supervised and the unsupervised anomaly detection. For supervised anomaly detection and the conditional invertible neural network, we apply a maximum likelihood optimization, and for the conditional variational autoencoder, a typical reconstruction loss with regularization. Those are typical. That is why we don't go into details here. For more details, I refer you to the article. But what is interesting is what we apply, which loss function we apply for unsupervised anomaly detection. Because our idea is that we want to assume a share of anomalous data. So we define a contamination C that represents this assumed share of anomalous data points, and we only use we use the above mentioned supervised loss function only for the samples with a training error below a threshold quantile, QC. So we want to exclude basically all anomalous data points when learning the mapping in an unsupervised context. With this approach, we exclude all other samples from the loss function. Given this trained generative method, we can talk about the application of our approach when we actually want to detect anomalies. So we again need calendar and statistical information as conditional information, as well as an input time series, in this case containing anomalies. Once it is sampled, we can use these two inputs for the trained generative method, which then uses the learned mapping to create the latent space representation of the input samples. These samples in turn can serve as an input for an arbitrary anomaly detection method that then detects the samples with and without anomalies. Since this approach is also available as code, we also evaluated it, and for the evaluation we came up with a certain experimental setting, and I want to share with you briefly share some details of this experimental setting, especially regarding the data and inserted anomalies, how we compared the different approaches, which anomaly detection methods we used, and how we evaluated them. For more details on the used generative models in terms of implementation, for example, and hardware and software, I refer you to the article. Let's start with the data. We use openly available data, in this case the electricity load diagrams data set from the UCI machine learning repository, and from this data set the time series MT200, because it's available for 3 years and it shows typical patterns daily, weekly and yearly. Since these data does not contain any labeled anomalies, we insert artificially anomalies, and in fact we do this for two groups of anomalies. The first group comprises technical faults. Technical faults violate the underlying distribution corresponding to normal behavior, and these technical faults have been identified in literature. We have 4 types that look like this: negative spike, 0 values positive spike, 0 values positive spike, negative spike, and a positive spike. We also have 4 types of anomalies from the second group, which is unusual consumption. For the unusual consumption anomalies, the values are from a valid range and represent in themselves typical patterns, but at uncommon levels. So we have an abrupt reduction, an abrupt increase, and we have a more smooth reduction and a more smoothly increase. Given this data with inserted anomalies, we then compare 4 different data representations that we create based on this data. So the first one is the unscaled data representation, which corresponds to the common approach of directly applying anomaly detection methods to the data containing anomalies. As I mentioned before, there's also the approach of using the scaled version of the input data. These are basically the 2 baseline data representations. We compare them with 2 latent space data representations. In the third case, it's here the third data representation. It's created by a trait CINN. And in the second case, here the 4th data representation, it's created by a trained conditional variational autoencoder. So the evaluation will compare these 4 data representations, but all data representations, of course, are applied for all data representations the same anomaly detection methods are applied. And we again differentiate here between supervised and unsupervised. We select these 7 supervised anomaly detection methods to cover a variety of methods, and we select these 4 unsupervised anomaly detection methods. We will also, since we consider supervised and unsupervised, we will also split the evaluation later on, the presentation of the results later on accordingly. But before we do this, I also want to share with you how we evaluate our approach. So we do it qualitatively and quantitatively. For the qualitative part, we use the t-distributed stochastic neighbor embedding. It basically maps high-dimensional data points into the 2-dimensional space, such that similar data points appear close together and dissimilar data points far apart. For the quantitative evaluation, we use 3 evaluation criteria: the detection performance measured by the F1 score, the detection robustness by means of different shares of artificial anomalies, and computational cost through runtimes, through measuring runtimes for the training of the generative models, finding the best performing hyperparameters, and fitting the detection methods. So let's have a look at let's start with the qualitative evaluation. So here you can see the TSNE plots for 3 data representations. We focus on scaled in the following because unscaled performs quite similarly. You also see both groups of anomalies, technical faults in the top row, unusual consumption in the bottom row. And for all of these combinations, you see 300 random samples without anomalies shown in blue and 300 random samples with anomalies shown in orange. And what you see is that, for example here, for the CINN latent space representation, that the samples with anomalies and samples without anomalies have less overlap here compared to the scaled data representation. And additionally, the samples without anomalies are in the center, and the samples with anomalies are clustered around these samples. So the orange ones are clustered around the blue ones. This observation is also generally visible for the unusual consumption. So let's move on to the first quantitative evaluation criterion, which is the detection performance. We will focus now first on the supervised methods. So what we see here is the F1 scores of the 4 data representations for each of the 7 selected supervised anomaly detection methods shown here. And what we observe here is that basically the CINN and the CVRE data representations all perform pretty well, and to be precise, they actually perform better. So the average improvement in the F1 score is 21%, but it ranges from 1% for the MLP to 52% for the random forest. This only considers anomalies from the group of technical faults. However, the same applies to the unusual consumption anomalies. And since we are talking about supervised detection methods, these results shown here are based on default parameters. We also performed the same experiment with best performing parameters, and the results were pretty much the same. So the same applies for unusual consumption and for best performing hyperparameters. So we can move on to the detection robustness. Here we focus on the latent space representation created by the CINN and compare it to the scaled data representation for the 3 best performing supervised detection methods. And what we see here on the left for the technical faults, if we insert different shares of artificial anomalies, it doesn't really impact the performance of the proposed approach, because the the latent space data representation created by the CINN performs consistently better by having higher F1 scores than the scaled data representation. For unusual consumption, however, this picture, is a little bit different, because what we see here is that for the MLP it's the same, but for the other two, the naive Bayes and the KNN, they perform similar. Both data representations perform similarly. What we can say about the third criterion, which is the computational cost, is the following. You see here again the 4 data representations, and here the 3 categories of runtimes we have measured. So let's have first a look at the runtime required to train the CINN and CVRE in a supervised way. We compare it to the times required to perform a hyperparameter optimization. You see that it's much lower for some methods, that it's about the same for other methods, and higher for other methods. If you compare to the detection method's training time, then you see that it's considerably higher. After having compared the rows here, the categories of runtimes, let's compare the data representations. So if we have a look at the hyperparameter optimization, we see, for example, for the MLP, that performing a hyperparameter optimization on the latent space, CINN latent space, requires less time than on the scaled data representation. However, for other representations, it's about the same or even higher. When looking at the detection method's training runtime that is required, we have a similar impression. That is that the training time depends on the data representation. For some methods, it's the same across all data representations, and for other it differs. So the latent space data representation can be quicker, but can also take longer in some cases. So let's move on to the unsupervised detection methods. First, again, let's look at the detection performance. Again, we see here technical fault and unusual consumption for the 4 methods, and for the 4 methods the corresponding F1 score. What we observe here is that if we look at the technical fault for the iForest, the latent space data representations perform better, and for the autoencoders about the same or in a similar way, but for the LOF they perform worse. And looking at the unusual consumption anomalies, we see that the F1 score of the latent space data representations are similar or lower. When considering the robustness of the unsupervised detection methods, we again use different shares of inserted anomalies, and for the technical faults, so again we compare the dots with the triangles, so the latent space data representation created by the CINN against the scaled data representation. And what we see here for the technical faults on the left is that the CINN latent space representation performs better for the iForest, similar for the autoencoders, and lower for the LOF. And for the unusual consumption on the right, the F1 scores are of the CINN latent space data representations are lower across all shares of anomalies. When having a look at the computational cost of the unsupervised detection methods, we again first look at the required training time, which is considerably longer than the time required for fitting of most of the unsupervised methods. This was basically now the comparison of the categories of runtimes again, but now having a look at the different data representations and the required runtimes, we again observe different implications. So for the autoencoders, variational autoencoder and autoencoder, the fitting is quicker fit is quicker than the training. However, sorry, not as a training, but on the latent space data representations, if we consider the I-force, it's about the same here, but for the last one, which is the LOF, it takes considerably longer to fit it on the latent space data representations. So it's a mixed impression. And given these insights, we see different points of discussion. So first of all, unusual consumption anomalies are quite hard to detect because they are similarly shaped. So even for a human, it's difficult to see them. This is why we highlighted them beforehand. We also observe, or our impression is that density-based anomaly detection methods could not be really suitable for this approach of using latent space data representations. The proposed approach can also be beneficial for the hyperparameter and methods training, because in some combinations it reduces the required runtimes. And in any case, you have to consider that the training of the CINN and CVRE implies, of course, additional runtime, so computational cost. And last but not least, for the unsupervised case, you of course have to select an appropriate contamination value. So to sum it up and to sum it up, basically, overall, using the latent space data representation enhances anomaly detection. So what we see is a clearer separation of anomalies and non-anomalous data in the TSNX plots. For the supervised detection methods, we observe an improved detection performance for both groups of anomalies. For the unsupervised detection methods, however, we only see a partially improved detection performance for the technical faults because they have difficulties with unusual consumption. And at the same time, we only have a moderate additional computational cost. For future work, we would like to consider multivariate time series, think about an integration of a latent space representation creation and the training of the detection methods, and improving the unsupervised methods regarding the unusual consumption, detecting unusual consumption in the latent space data representation. Thank you for your attention. I also would like to thank the funding organizations, Helmholtz Association and DFG, and here are the references for completeness. Thank you very much, and I'm happy to answer your questions.